We begin with a simple binary categorical variable, gender in emergency room patients. In a survey of a random sample of 450 emergency room patients at a certain hospital, 275 were female and 175 were male. Our raw data consists of a list of 450 observations containing the gender of each patient. We can summarize this data numerically using a frequency distribution. This table could also be considered a visual display, but we could also create a pie chart or bar chart if desired. In practice, we would summarize the results presented in the frequency table in a short sentence, or possibly in a large table containing this type of information for many variables in the study. Here is an example of such a table from a different study. Often the purpose of this type of one-variable analysis will be to give an overall descriptive summary of the patients in the sample. How well does it represent the population to which you want your results to apply? The closer your sample matches the population of interest, the less limitations there are in your results. Here we see that among the 450 patients surveyed, 61.1% were female. Suppose we wanted to determine if there is evidence that the true proportion of female patients in this ER is different from 50%. When checking the sample size for confidence intervals, we check if n times p hat and n times 1 minus p hat are both at least 10. Since 450 times 0.611 and 450 times 1 minus 0.611 are at least 10, we can construct the 95% confidence interval for the true proportion of females using the equation we presented. The appropriate confidence multiplier in this case is from a normal distribution due to the fact that for large enough samples, the distribution of all possible p-hats, the sampling distribution, will be approximately normally distributed. This confidence interval consists of our estimate plus or minus our confidence multiplier, 1.96, times the estimated standard error of our statistic. The resulting interval is 0.566 to 0.656. Thus, we are 95% confident that between 56.6% and 65.6% of all ER patients at this hospital are female. Based upon this confidence interval, since 50% is not a plausible value, we can conclude that the proportion of females is not 50% in this ER population. In fact, the confidence interval estimates the true proportion to be greater than 50%. When checking the sample size for hypothesis test, we check if n times p0 and n times 1 minus p0 are both at least 10. Since 450 times 0.5 and 450 times 1 minus 0.5 are at least 10, we can also answer the question using a hypothesis test with HO p equals 0.5 and HA p is not equal to 0.5. We calculate the test statistic as illustrated, giving z equals 4.71. This test statistic tells us that our p-hat is 4.71 standard errors above the hypothesized value. This is extremely unlikely for a normally distributed quantity. The p-value is basically 0 for such a large z-score under the normal curve, and thus there is enough evidence to conclude that the true proportion of female patients in this ER is not equal to 50%. Remember that the p-value is the probability of obtaining a result as or more extreme than our data in the direction or directions of our alternative hypothesis, assuming that the null hypothesis is true. For a little better practice, let's suppose we had similar evidence from a smaller sample size. What if we took a random sample of 100 where 61 patients were female? Then the test statistic would be z equals 2.2. Since our alternative hypothesis is two-sided, to find the p-value we need to calculate the area both above 2.2 and below negative 2.2. Our p-value is 2 times 0.0139 or 0.0278, which is less than 0.05, and thus we reject the null hypothesis. There is enough evidence to conclude that the true proportion of all patients in this ER who are female is not equal to 50%. Notice that when we conduct hypothesis tests in practice, they are usually two-sided. Most definitely, the only one-sided tests which should be conducted are ones for which you know before you collect your data that you wish to prove only one direction. Sometimes this is the case. We want to prove our drug results in weight loss, or we want to prove our treatment increases red blood cell count. The main point is that you cannot change your hypothesis to a one-sided test after you see your data. In this instance, we can't decide after seeing that 61% were female in our sample to change our desired alternative hypothesis to greater than instead of simply not equal to. Be sure to state your hypotheses based upon what is provided in the scenario, not based upon the information you are provided about the sample. Also notice that a disadvantage of conducting a one-sided test is that if it turns out the truth is the opposite of what you desire to show, your test will not be designed to discover that information. And this is certainly one reason that the standard practice is to conduct two-sided tests, followed by confidence intervals for the estimation of any effects of interest. Before moving on, notice that since we rejected the null hypothesis, we could have made a type 1 error in this case. To describe this error in context, we could say, it is possible that we could have concluded the true proportion of females is different from 0.5, when in fact it is equal to 0.5. To review the p-value calculation for one-sided tests, we will consider a simple example of tests about the fairness of a coin. Suppose you have a lucky coin that you believe lands on heads more often than tails. Then your hypotheses would be HO p equals 0.5 versus HA p greater than 0.5. Suppose your friend, who has seen you use this coin on numerous occasions, thinks you're crazy. And if anything, your so-called lucky coin lands on tails more often than heads. Then your friend's hypotheses would be HOP equals 0.5 versus HAP less than 0.5. Since it is your lucky coin, it is decided to allow you to flip it 100 times. You do, and you get 48 heads on 100 tosses. Now, it's fairly clear that based upon the results of this sample, there is no evidence that p is greater than 0.5. In other words, we expect to find a very large p-value for that alternative hypothesis. There is some anecdotal evidence to support your friend's claim that p is less than 0.5, but we will need to take into account the sampling variability in 100 tosses of a fair coin to assess if this is enough evidence to support your friend's claim. Let's calculate the p-value for each test using this sample to illustrate the process. Since your alternative hypothesis was greater than, the p-value for your test finds the probability of obtaining a z-score such as that in the data or larger, as these are the values that are as or more extreme in the direction of the alternative. Your p-value is the area to the right of negative 0.4, which is 0.6554. Your friend's alternative hypothesis was less than. The p-value of this test finds the probability of obtaining a z-score such as that in the data or smaller, as these are the values that are as or more extreme in the direction of the alternative. Your friend's p-value is the area to the left of negative 0.4, which is 0.3446. In both cases, there is not enough evidence to reject the null hypothesis. We didn't need to know the p-value to know this was the case for your test, but for your friends we needed to know how rare this value was in order to determine if there was evidence to support the claim that p is less than 0.5. If you and your friend had decided prior to collecting your data to simply test the two-sided alternative, the p-value for this test would have been 2 times 0.3446. It could be that the coin is really fair, but then again, maybe not. We aren't able to prove the null hypothesis. We only know that this data does not give us evidence to reject it in either direction. In this case, since we failed to reject the null hypothesis, it could be that we have made a type 2 error. In context, we could say, for your test, it is possible that we concluded the true proportion of heads on this coin is not greater than 50%, when in fact it is. This would make you happy. For your friend's test, it is possible that we concluded the true proportion of heads on this coin is not less than 50%, when in fact it is. And for the two-sided test, it is possible that we concluded the true proportion of heads on this coin is not different from 50%, when in fact it is different from 50%. Let's take this opportunity to review the binomial distribution and use our ability to calculate binomial probabilities to look at the what-ifs of this situation. We will illustrate the calculations under the null hypothesis visually and then present a full set of results for discussion. we will go back to using a binomial distribution to calculate probabilities using n equals 100 and p equals our current guess at the truth. Under the null hypothesis, we assume p equals 0.5. Now we calculate three probabilities: the probability that x equals 48, the probability that x is greater than or equal to 48, and the probability that x is less than or equal to 48. In this particular case, where we assume p equals 0.5, the last two probabilities are the exact p-values of your test and your friend's test, respectively. We applied the exact distribution instead of approximating it by the appropriate normal distribution. Here we find that if the coin was exactly fair, there was a 7.4% chance that we could obtain 48 heads out of 100 tosses. There would be a 38.2% chance of getting 48 heads or less, and a 69.1% chance of getting 48 heads or more. Notice these last two probabilities do not add to 100%, as they both contain the probability that x equals 48. Now we will start assuming other values for the truth, which are not the null hypothesis. The question is, how large or small does the true proportion have to be before it becomes very unlikely that this would happen? This may help you see how all of this fits together and help you understand a little more about how we calculate type 2 errors and power. Although the probabilities we will calculate are not directly related to either type 2 error or power, they will be calculated through a similar process, by assuming a value for the truth and then calculating probabilities based upon that assumption. I didn't use the applet for these calculations, as it would have taken quite a while. I used an Excel formula, binom dist, and the ability to fill down to obtain this table very quickly. The row in bold represents the probabilities we calculated on the previous slide, where we assumed the null hypothesis is true. If we look at the probability that x equals 48, we see that it is largest when the coin's true percentage is 0.48, as we would expect. It is fairly likely to happen if the true value was 45% through about 52 or 53%, but it does not become extremely rare as an individual outcome until we get to true values approaching 60%. For example, if the coin were 60% heads, there would only be a 0.4% chance we could ever see 48 heads in 100 tosses of the coin. Considering it from your perspective, it is your lucky coin after all. In order to really investigate how rare this would be, we should consider the probability that x is less than or equal to 48. Looking in that column, we see that if the true probability of heads is 54%, overall there is still a 13.5% chance of getting 48 heads or lower in 100 tosses. Not very rare. If the true probability is 57%, that probability drops to 0.044, which is somewhat rare. And when the true probability is 60%, there is a 1% chance of getting 48 heads or less in 100 tosses. Since we found a sample with x equals 48 for this coin, we can see from this table that there are numerous values of p for which we could easily have seen our result. Besides being a quick review of the binomial distribution, the final conclusion of this example is, just because we fail to reject the null hypothesis doesn't mean the null hypothesis is true. In this case, with 48 heads and 100 tosses, p could easily be 0.55 based upon the results in this table. In fact, the 95% confidence interval would range from 0.382 to 0.578, which says that any value between 0.382 and 0.578 is a plausible value for the true probability of heads on this coin. You could still be correct about your lucky coin, but so could your friend. More data would be needed to settle this argument.